You can everyone. So our project is on using 3D craniofacial morphometry data to improve dysmorphology. And so I'm going to start, and then Rich is going to take over, and then Benedict is going to talk about our data analysis. Keep it close. A rock star. So we have 4 aims in our project, which are the first one is to build a 3D facial scan library of dysmorphic syndromes. And so I'll give you an update on where we are with that. We've been making a fair amount of progress. And then the following aims are using the data. So aim 2 is extending the geometric morphometric toolkit to enhance discrimination of dysmorphic faces. Aim 3 is validating and extending dense surface modeling approaches to syndrome diagnosis. And then aim 4 is developing a prototype tool to assist in diagnosis of syndromes. So for aim 1, our initial plan was to have several sites, including Denver, San Francisco, Calgary, and London. We had to drop London relatively early because there was no IRB approval. So our first 3 sites were the ones represented here. And then we've added a number of collaborators, which has been really great in terms of increasing recruitment, including in Milan, Australia, at Stanford, and LA. And Pedro Sanchez, who's here today, is the head for our CHLA site. We currently have approximately 3,300 enrolled participants. I say approximately because we're adding more every week in our clinics. So this was as of about a couple of weeks ago. And approximately 1,000 of these have been enrolled from patient gatherings, which have been really useful because these are gatherings of very, very rare syndromes, of which there might be only a couple of dozen examples in the world. And so they're not patients that would necessarily wander into any of our clinics because they're such rare syndromes. And we have some examples of that on the coming slides. So last year we attended 17 of these patient gatherings, and this year we're planning to attend 23, including a large number of these are new meetings that we haven't attended before and that have, again, some of these very rare syndromes, so that will help to populate the database. And as you'll see on the next slide, there's already a very large number of syndromes represented. This is, in our, as far as we know, the largest such collection of images that exists. So I know this is probably kind of hard to read, but I'll just make a couple of points about this syndrome distribution and then turn it over to Rich. One of them is that we have, as I said, a very large number of syndromes, and obviously there's a variation in the number of images per syndrome. Some of them, such as Down syndrome, which are more common, we have hundreds of images, and then some of the ones that are more rare, we have a smaller number. Our goal over the remainder of the project is both to increase the overall number of syndromes as well as in those syndromes that are rare to increase the number that we have. As Benedict is going to actually talk about, we've been thinking a lot about what the minimum number of images that we need for a given syndrome to obtain useful information, and Benedict actually has some new ideas about how we could decrease that number for syndromes that are rare. So I think at this point I'll turn it over to Rich, who will continue to talk about the syndrome distribution of the market.
Thank you, Rick. So we've been spending a lot of time on the database and the metadata. And I think that, there's a major nosology problem in the field of human genetics, or as the layman would say, garbage in, garbage out. And cleaning up the database and what is available for use is requiring a lot of our effort at the moment, and probably to continue. And the problem is that we have a lot of different people entering data, and about half of them turn out to have dyslexia. And databases are very intolerant of spelling errors, of adding a space inadvertently when there shouldn't be one, of using Arabic numbers instead of Roman numerals, changes in clinical nosology, and anything else you can think of that introduces variability into how data are represented. We haven't found any efficient way to deal with this other than manual curation. And this is really what led me to suggest that we have a session on this tomorrow, because I think all of us dealing with human data are probably dealing with the same kinds of problems. And if you aren't, you either need to or you need to tell me how you're doing it more efficiently than we can. This is just an example. I've been spending a lot of time lately on the OMIM, Online Mendelian Inheritance and Man database, sort of manually curating it, and so that we can therefore manually curate our own metadata, which, by the way, was the best we have at the moment, which is pretty good, was just uploaded to the hub the other day, sort of a newer iteration. And just to show you, there are currently, as far as I can tell, 18 recognized subtypes of Ehlers-Danlos syndrome. Obviously, since they all have the same name, Ehlers-Danlos, somebody initially lumped these all together. There's been a lot of splitting. There have been multiple changes in nosology over the years, and some clinicians enter into the medical record using the old or one or another of the old nosologies that are no longer considered valid. That will then get picked up and entered into our data. And ultimately, all of that needs to be cleaned up and consolidated into whatever nosology we adopt. And the OMIM numbers give you a unique identifier, but they're far from perfect and they're far from complete. And there's also a lot of garbage in there, it turns out. So this is the kind of problem that we're dealing with. And I've done this now for about 10 different syndromes where there are many, many subtypes. And teasing them all apart is not so easy. And you can see that under 130000, there are 3 different genes that represent that syndrome. And one would normally expect those should be split out and each have their own syndrome identifier because they're really different genetic diseases. So we'll be talking quite a bit about this, I think, tomorrow. See where we are here. Sorry, keep the mic. Oh, you're right, I can hear it. I think this is really just going through the cameras that we've switched over to 3D MD. We still use the Gemini cameras for extras when we have too many clinics happening on the same weekend in the summer because they all tend to schedule at the same time. And so we'll have to address that as well. We have a data pipeline then in which we collect samples at clinic or patient meetings. There is a fair amount of QC of images that still has to happen, even with 3D MD, as you'll hear. Those go into the Calgary image database and ultimately to the hub. At the same time, the metadata goes into a restricted database. There is clinical review and update, and ultimately those go to the hub either. We thought we were really smart in part of this nosology curation. Benedict and I developed a whole series of drop-down menus so that people would be forced to choose. Just learned the other day, because I'm running a very large international meeting this summer, I was looking at registrations. Academics have a 1% to 2% error rate in use of drop-down menus. They either hit the one above or the one below. And as I've said, the data sets are intolerant of that kind of error. And so we've actually, over beers last night, decided we need to get rid of the drop-down menus that we just spent so much time creating and think of some other way of entering data, getting people to enter data. So it is very problematic. Metadata are stored in a SharePoint database. All of us have access to editing it. And then that is what gets sent to the hub. We haven't really worked out automated upload to the hub, and probably that's not worth the effort, I suspect. So Benedict is going to take over and talk about what we're doing in terms of data analysis.
With dyslexia, I should probably own up to that. So we have currently, as mentioned earlier, nearly 3,500 patients, 3,285 actually, the exact number of it this morning in the database. We have landmarked and processed approximately 3,500 cases. Last year, we recruited Dr. Neil Corporate Group to be an imaging informatics specialist to replace Washington Neo, who was initially involved. And that actually has led to a number of improvements that I'll talk to in a little bit. And I'll present some preliminary data on first task that we asked Niels to take on, and that we've been working on really hard now for the last year, was actually automated landmarking. And that may seem surprising because we developed automated landmarking as part of FaceBase 1, but it turned out that method was not sufficiently robust to be used in the dysmorphic basis. That method relied on automatically finding control points and surface features of space, which seemed appealing because it created a set of independent landmarks. But the problem is that it isn't easily extensible to a large range of morphological data. And so we had to go to what is actually a more accepted or more generally used approach, but ultimately would be a more useful one, which is to use a combination of rigid and then nonlinear registration to morph every face to map it, transfer the points to a face, to every face, and then restore the face to its original configuration, thus changing the landmark configuration of every face. The advantage of this method is that it doesn't limit you to a particular step of landmark. You can obtain any kind of quantification from the faces once you've done this nonlinear registration step. So nonlinear registration is really the key that will generate both landmark data, dense representation data, and also surface data. A major issue that we've been dealing with is this has to do with the quality of the data. And it's no matter how good the analysis methods are, all of these methods are sensitive to the quality of the input data. Some of you might remember the various problems we had with FaceBase 1 data and the earlier generation cameras we had at that time. We thought that when we went to 3DMD, all of those problems would go away. At least that's what 3DMD told us. Turns out, though, that there are different problems with those cameras that have required a lot of work to overcome. And for this, for a tool that's based on 3D imaging to be clinically useful, relying on physicians or medical geneticists in the clinical setting to be manually editing images and stuff. So we have to find ways to get around these things in an automated way. So the two basic problems are cropping and orientation. So this image here shows you kind of problems you get cropping. All of the information that's outside the face, if there's too much of it, or if it's really unusual, can end up producing a problem with the initial alignment of the image. And this is the problem has to do with orientation. So the face is really far from being aligned to the camera, then you end up also with a registration problem. The graph here, with the lower graph, shows the improvement that you get in the registration result once you fix this initial alignment problem. So currently, we're actually aligning images manually, which is not optimal. But we have actually, just in the last couple of weeks, made significant progress in terms of developing automated alignment. Automated alignment is going to be an initial stage before we even start the registration process. All of this work on automated landmarking is being worked up for publication, led by Niels Worker. But there are additional directions that we will take with this. Of course, we want to make the landmarking system sufficiently robust to be used in this way. We also want to address the question of how necessary is it really to go to 3D imaging. This is a question that's often asked. It's of course much cheaper and easier to do 2D imaging. My sense is that 3D imaging will become cheap and easy enough in the future that this may no longer be a question. But we are asking or comparing our data to 2D morphometric data to see how it performs. And we're also moving towards more quantifications that are directly derived from the 3D image data. The third aim of the project has to do with validating and extending dense surface modeling approaches to syndrome diagnosis. So this is moving towards using more of the image data in this parse of landmark. And one of the reasons we chose Niels to the project is that he is an expert in statistical shape modeling, which is one of the ways in which one can do this. There are other methods out there, such as those developed by Peter Hammond and Peter Fraze, and we are also exploring the use of those. So here is an example of work that's been done fairly recently. Corey Lim and I, who works with Niels and myself, has been working on getting direct quantifications from the surface maps, which of course is a huge amount of data. And so she initially thought to break down the face into regions just in order to manage the data. And it turned out that the regional information was in many ways more useful when viewed in isolation. So now we are exploring the option of zeroing in on particular parts of the face that are diagnostic by certain syndromes. Currently, she's doing this somewhat arbitrarily, but the idea is to actually follow recent work by Peter Fraze to use the full variance matrix of the face to identify the random parts of the face that have stronger signals associated with them. And the initial results from this are encouraging. So, for example, in a sample of 25 large patients and 42 Down syndrome patients, she was able to classify these patients with 91% accuracy based on direct quantity. So this is not using landmarks. This is direct analysis of the surface cases. Another direction that we're taking is using machine learning, and this is applied both to the landmark data and also to the quantifications that Troy is getting from the face. So here's a first pass analysis is based on the sparse landmark set, 49 3D landmarks in the face. And the graph right here shows the difference between the performance of this method and more traditional geometric morphometric based methods, common various based approach to classification. And this is also encouraging, and in particular, it addresses a problem that Steve mentioned earlier, which is the sample size issue. Some of our syndromes, we have very few individuals. And so, are we ever going to be able to do anything useful in a syndrome where we have, say, fewer than 20 worldwide? Well, with machine learning, potentially you can. There are issues with overfitting, et cetera, but the initial results are encouraging. For example, Klinefelter syndrome, which is very subtle, with a training set of weights and a foundation of 7. David Aponte, to this work, was able to correctly classify 7 out of 7 Klinefelter patients. That's pretty good. Okay. I think I'm probably running out of time, right? So okay. Okay, I'll slow down. Well, the fourth aim was to take this stuff, well, basically take this stuff to the next step, which is to use the 3D image data to diagnose syndromes. And I think this really has two components. One is just building the analysis framework, the underlying theory and method that will enable you to take 3D images of faces and diagnose syndromes from them. And the second piece is really building the framework in which a software program could be created that would do that. They're actually quite distinct things. But we are working on both. We did it in this project plan to actually produce a usable or a commercially viable software package. So that's still an open aim that we are pursuing. We are submitting proposals to get that funded, but that is the ultimate aim. One of the steps that needs to be done in order to use faces for syndrome diagnosis is to quantify, use, or remove as much of the ancillary covariant information as possible. We know, for example, that facial shape co-varies with height. We know that many syndromes affect height, so how much of that variation in facial shape and syndromes that affect height is due to the fact that these patients are shorter or taller, and how much of it is due to the effect of the syndrome itself. People with Marfan syndrome, where their faces the way they are because they're really tall or because they have Marfan syndrome. And in order to distinguish that, you have to quantify the covariation associated with height and analyze it separately from the variation associated with syndrome. So it turns out that this is actually quite complicated. We've recently submitted a paper that's now in review, and it's in collaboration with Seth Weinberg's group, so for example, a spoke-to-spoke collaboration, in which we've analyzed a variety of these covariates and their interactions in determining facial shape, and that's really key to being able to use them for syndrome problems. So age, of course, is a covariate that affects facial shape, and you would be surprised to know that it relates nonlinearly to facial shape. So you have to in a sample that includes both children and adults, use nonlinear correction to remove age from the sample, which of course we did in the analysis that I'm going to show you just now. But the other thing is we have to get a handle on just how much variation in facial shape there is that can be used to diagnose syndrome. So this is actually the stage that we are at now. We said earlier about 3,200 patients. The landmark data is catching up with the image data set. We currently have a usable set of about 1,700 individuals that we're working on. And I'm happy to tell you, although Rich wasn't impressed when I told him this, but I was impressed, which is that 16% of the total variation in facial shape is due to syndrome. And if you consider the fact that most of us look like ourselves, and secondarily like our parents, and probably thirdly like something else, for example, syndromes, that's a large amount of variation associated with the factor. Put that in context, roughly 4% of facial shape associated with sex. 10% is associated with age from birth to adulthood, about 5% from age 4 to 20. 5% of facial shape variation is associated with a difference between Tanzanian and South American and European-derived children. So these are large factors that we would think of as being big influences on the shape of the face, and yet they are much smaller in magnitude than variation associated with symptoms. I'll show you a series of 3 canonical variance graphs here that I produced actually on the way here, and didn't have a chance to produce 3D morphs to go with them, so I apologize for that. I grouped the syndromes into categories because there are so many that it would be hard to make sense of these graphs without that fact. But you can already see some interesting signals. So for example, the trisomies are off here in this area. Most of this is Down syndrome, and that's on the first canonical variant. Look at the second canonical variant here, the blue region. This is all neurocristopathies, Treacher Collins syndrome, and other related neurocristopathies that are separating, actually, interestingly, not just separating from controls, but also separating as a group, which is quite interesting. And here's the 5th and 6th canonical variant, also showing some of the smaller effects. And so there's a lot of variation in the data associated with syndromes. And so this is just using geometric morphometric methods, so canonical variance analysis to classify syndromes based on the data that was used for that CDA plot. And these are the syndromes for which we have more than, or for which we have 10 or more individuals in the landmark data set. And you can see here that we're getting an overall classification rate of 83%. And so that's sort of a baseline. The hope is that by using fancier methods like direct quantifications from surface maps or that in combination with machine learning, that we're going to improve on 83%. But I think 83% is a pretty good start, actually. And if you look at the syndromes that you're able to classify here, some of them may not be surprising. I was initially quite concerned, for example, that we had a hard time distinguishing relatives. Relatives are unaffected controls that have a patient in the database, until I realized that of course not, because we have 2,500 controls from the Pittsburgh data, and it would be a bad thing actually if the relatives were different from the controls. So that was encouraging. And the one syndrome where we seem to have a lot of trouble is actually the one that Rich was talking about earlier, Ehlers-Danlos syndrome. And that's, I think, a combination of the fact that it's facial shape effect is very subtle, but also heterogeneous within one thing. If you classify something that is one thing, of course, you're going to do a bad job of trying to classify it. There's a pattern. There are patterns in the relationships among these syndromes. If you can see that here in this plot that shows the degree of similarity, the degree of distance rather in morphology between syndromes. Some of the ones with big effects like Costello and Gown syndrome over here have large circles. That means that they're quite different from others. And here they are grouped by similarity or clustered by similarity. So what's driving that cluster, it's important to note, is not the magnitude of the big effect, but rather the similarity. Some of the patterns you see are interesting and actually encouraging. Newman and Turner coming together is expected and interesting. Kleinfelter's Ehlers-Danlos controls and relatives grouping together is encouraging. Also Markman and Louis Dietz, both connective tissue disorders, being very similar to each other is interesting because you have height as a driving covariate that will be producing an apparent difference between these two, but they actually are quite similar in the control for that. I have no idea why Down syndrome, which is very, very different in terms of the magnitude of the effect, is somewhere there in the middle. But yeah, we are beginning to work our way through this. There's a lot of signal in these data, and we're quite confident that even with current methods that we can build a useful tool, that we will be able to extend those methods to improve on a tool to diagnose symptoms from facial shape. Any questions?
Hi, Somnath Gara from US. So if I understand this correctly, this 80%, you are classifying all these groups?
Yeah, so
that's amazing.
That's right. So the classification task is that you have an individual, you pull that individual out, and you classify them into the correct group. So that includes controls. And it's not done as a two-step process. It's not, does this person have a syndrome or not? And then if they have a syndrome, what do they have? It's actually because what group do they belong to, including controls.
Just by way of comparison, there are 2 published papers studying the ability of board-certified dysmorphologists to correctly classify patients. One had all patients had syndrome in the study. One had 7 different choices. The other had 25 different choices. They both got the same answer, and then he was at 75%. So 83 is not bad.
So is it control versus each of the symbols separately, or
sorry?
Is it control versus each of these syndromes separately, or
it's
all of
each
them?
Patient versus the entire classification scheme. So you have a patient, does this person have Downs, Costello, feature Collins, whatever?
And that's 82%.
83% of the time you get it correct. And of course, there are sample-dependent effects here, right? So this applies to the construction of our database. It doesn't mean that if you have it doesn't mean that if you have 1,000 unknowns in a clinic, that you would do 83% accuracy with 3D facial imaging in a sample of unknowns, because unknowns are going to have a different makeup in this sample. For example, we include Down syndrome.
These are not cost value.
No, they're cost value against our sample. Yeah.
I probably don't want to fixate too much on the 83% number, because this is very recent work that we're going through. Okay. I'm not.
Yeah.
Thank you. Never seen that categories, but it's great.
It's encouraging. Okay. We're trying to get too ahead of ourselves.
I think Chad said icons go on. Are these diagnoses based on molecular diagnosis, or this is phenotype? Because there's a lot of genetic heterogeneity.
I'll let Rich take that one.
So they're a mixture. And we initially had hoped that all subjects would be molecularly validated. Turns out that's not how clinicians operate, and that's not how insurance companies operate. So when we can get molecular diagnosis, and particularly important in terms of subcategorization, we do. But frankly, we take the best information that we have, and we've been pretty hard on some of the people who have been submitting, that was us, submitting samples and trying to get them to be more accurate, and it's simply the most accurate information that we can get.
Yeah, like Rich was saying, it's very difficult to have everything fully standardized, because there are cases where there's a spectrum. Sometimes there's conditions that people never do molecular testing for, because the diagnosis is so obvious. There's others, like you were saying, where it's very difficult to get and pay for. And we've been struggling with this issue actually for the whole project, because we're simultaneously trying to build as large of a collection as we can, while making it as good of a collection as we can. So those are things that we're balancing.
You might analyze it.
Yeah, so we've just, this stuff that Ben has been showing, it's relatively recent for our group, and there's a lot of different ways that we can slice and dice this. So we could look And we're starting to. So right now, what Benedict is putting together is kind of our initial report, just based on an overall look at all of the data together. But then we want to get in and do things like what you're suggesting, and look within syndromes or compare, for example, just among the restopathy and things like that. And as the data are going to be, they've been deposited and we continue to deposit, people can also start to do these things.
I think along those lines, one of the kinds of things we're thinking about now that some of the numbers are pretty big is what are really useful things that one could do with the data now. So, and one of the reasons I'm focusing on Ehlers-Danlos syndrome is Ehlers-Danlos syndrome type 1 these days is a gemisch. It's probably a lot of different things rolled together. Nobody's been able to find genes for it. The benign, what used to be called benign hypermobility. Could we actually classify more accurately than people are able to do easily, even within that category, because it represents a lot of patients. So that's an area where we might be able to make a real contribution right now, and why we're really focusing on it.
The use of 3DM, the automated landmark program they've recently. Also, Phase2 gene, done a lot of 2D imaging and generating.
Wasn't there where the 3D had on the landmark program? I'll look at that. The phase of the gene that you're talking about.
We recently had it downloaded. Yeah,
So the 3DMD does have an automated landmarking protocol, Patrick. It doesn't work for dysmorphic faces, period. So that's one problem. A second problem, with respect to FDNA and use of 2D images, there are a few things that we would like to do that are sort of extensions of where we are now. Benedict mentioned comparing 3D and 2D in a very formal way. We actually would love to compare whatever we do to FDNA. We're not sure they would be so happy with us doing that, but we talked about it. Another thing that we've also talked about doing, it's going to be a little hard to organize, but once we get to a point that we're doing better, we would love to actually assemble a group of board-certified clinical dysmorphologists and do a formal comparison of all of these methods, including clinicians.
Just the comments I made about FDNA is that we did approach that initially. I think people heard about that in one of the first meetings. And the problem with them is that they do not want to share any of their data or any of their algorithms. And so it makes it very difficult. It looks like there's a very one-way interaction. And so we're trying to think of other ways that we can actually, so we think it's important to compare 2D and 3D in some way. And the bias that we have, which I think makes sense, is that 3D is going to have a lot more information than 2D. So it's very difficult to imagine that 2D will in the long run be, which is very saying that it's going to get easier to get these kinds of images. But that company in particular has been incredibly challenging, and I think not very community oriented also in the way that they're approaching.
And by the way, we have a comment from the webcasting. I think this is Melissa. I'm having one comment that might be interesting is to compare these results to other disease similarity approaches. Also, it would be great to coordinate with the Minerva consortium that is focused on these comparisons of 2D and 3D as well.
Let me one comment about automated landmarking, and that's that it's relatively easy to write a program that will put dots on a 3D image. Very difficult to do that well. And so there are lots of programs out there. Very few of them actually, well, none of them work as well as a really good manual landmarker. And one reason for that is that whenever you have an algorithm that uses something like nonlinear registration, transfer points from the atlas to every individual mesh, there's going to be a compression of variance, and there's also going to be an atlas effect. this was the thing that was so appealing about Washington Neo's method, because it actually de novo identified every individual point on the image. The problem is that it wasn't sufficiently generalizable, and we couldn't figure out a way to do it. We simply haven't been able to replicate what a human does when they pick points with a computer. And you should be careful to be a sophisticated consumer of automated landmarking methods, because every method out there produces artifacts, and you have to understand what those artifacts are.
Then you found that 10% of the relatives, is that how 10% of the relatives showed up in that graph. Do you have genetic data that suggests that those are mildly or grossly unaffected carriers?
Yeah. Evolutionary biologists would say, yeah, those are probably heterozygous. I don't know.